In today's lesson, we're going to be learning and applying Kirchhoff's laws to circuit problems. Gustav Kirchhoff, if that's how you pronounce it, was a very prolific German physicist who was around 1824 to 1887, who contributed to understandings of electric circuits, but more importantly, spectroscopy and something called black body radiation, which we will look at in topic 8. But generally, we're just going to look at the work that he did in electrical circuits. Here's a quick warm-up. Have a look at this circuit and see if you can figure out which meter is not connected as it should be. Stop the video and have a go. Hopefully you can see that this voltmeter is completely in the wrong place. It should be in parallel. I assume that it is working out, it's trying to find the potential difference across this resistor, so it should be in parallel. So the answer is 4. Well done if you got that. Now we're going to look at Kirchhoff's laws. There are 2. The first one is one that you're actually already using, but it just very much summarizes mathematically what happens to current in series and parallel. We're not going to think about series and parallel anymore. What we're going to think about instead is junctions and loops. What do I mean by a junction and a loop? Well, if I show you a circuit, let me fast forward until I find a complex circuit. Fast forward. Here we go. Here are some complex circuits. A junction would be where we see the wires splitting into various directions, right? So this would be a junction. And by a loop, what we mean is an entire circle. So this would be one loop, this would be another different loop, and this would be a third loop here. So no more series and parallel. We're going to think about loops and junctions. So let's start with Kirchhoff's, I think that's how you say it, first law. And his first law, if I can find it here, is that the sum of currents flowing into one of these junctions is equal to the sum of the currents flowing out of that junction. So what goes in must come out. This is a great example. If you have 8 amps flowing into a junction, then you will have a total of 8 amps flowing out of a junction. So here we have 3 amps in one direction, and 5 amps coming out. Again, they're both coming out of the junction, and 3 plus 5 equals 8. So we see that Kirchhoff's first law is respected. Now we can write that mathematically using summation. Can't get too close with my cursor. I'm going to wait for that to go. Here we can see summation of current in equals the summation of the current out. Now, this is written differently on the data booklet. What it says in the data booklet is that at a junction, the total sum of all the currents is equal to 0. So if we go back to the previous example, we can see that the total is equal to 0. It will be 8 minus 3 minus 5, right, will give you 0. That's the net total. So that's rule number 1. All right, so try this question. You've got 10 amps flowing into the junction, 3 and 3. What is the direction and the magnitude of the current flowing in this branch? Stop the video if you have to before you check the answers. Okay, so what you can see here is it's written out like an equation, right? You've got the summation of current in, which is 10, equals summation of current out, which is 3A plus 3 amps plus an unknown, and then you would rearrange to find the answer. That was 4 amps. So that's basically straightforward. So let's go on to Kirchhoff's second law, which basically states that energy is conserved within a loop. Right, so we've moved from junctions now to loops. For any given loop, the energy coming in to the circuit, which we refer to as the electromotive force, the EMF, is equal to the energy coming out of the circuit, which we refer to as the potential difference. So here we have a loop, and you have energy supplied by batteries Here we have 5 volts of energy per unit charge plus 13. So that gives us a total EMF of 18, right? And then we have some PDs here. Now it is a little bit more complicated, and I'll go over how to solve the problems in a minute. But let's see if we understand the equations. The energy in per unit charge equals the energy out per unit charge. And in your data booklet, that is written differently. It's written like this. The summation of the voltage, now remember voltage was a general term, right? Which included EMF and PD, either. What it's saying is that the total in minus out will be equal to 0. So before we tackle an example, let's have a look at some rules that we must follow. When you're applying Kirchhoff's second law, you must choose one loop only and disregard everything else that's going on in the circuit. I'll show you what I mean in a minute. Secondly, you must have current directions labelled. Which way is the current flowing? Now, if you don't have those arrows drawn, then you have to guess. And the best thing to do is to take a sensible guess using the conventional current. I'll show you what I mean in a minute. And then thirdly, tackle the problem starting at any given point, if possible using the power supply's positive terminal as a starting point. So we kind of have two directional issues going on there. On the one hand, you need to have your current directions. On the other hand, you need to have a direction for you to solve the problem. You need to go round in a circle because it's a loop. Which way shall I go? Well, this is what I'm going to show you. So what do we mean by that? Let's have a look. The first thing you need to think about is the current direction. Let's see if it's drawn. It's not drawn on here. I need to explain it. So we have, firstly, PD equals EMF, right? So we're going to look at our EMFs and our PDs. We need to figure out which way is the current flowing, right? Now, I'm going to use conventional current, and I'm going to assume, let's have a look, conventional current is what would happen if we had a positive charge in the circuit. So it's kind of anti-common sense. This long stick is the positive terminal. So if I was a positive charge, I would try and get as far away from this positive terminal, because positive and positive repel, and I would move in this direction. Now what does that tell me? That the current is moving in this direction. So label the direction of the current this way, right? And then secondly, I've got to solve this problem. And in order to solve the problem, I need to choose a direction to go in. So I'm going to actually use the same direction as the one I've just previously mentioned. The direction from the positive plate of the batteries. Now I'm going to start here and I'm going to see what my total EMF is. EMF is 13, because this is EMF. And I'm going to move around to solve the problem. I'm going to see if there's any more EMFs in this circuit. Oh, here's another EMF. Now, if this stick thing, long stick positive terminal, had been over here, then what I would have is a subtraction. I'd have had 13 minus 5, because the push of the 5 would be in the opposite direction. So I need to do it like this. 13, go round in this direction. I found another EMF, and it happens to be in the same direction. So I add them. And I end up with 18 volts of EMF. Let me go round the circle to see if there's any more EMFs. There's no more EMFs. So this bit is done. And now I'm going to look at my PDs, where the energy is leaving the circuit. My first PD is this one. And I can write this down in two different ways. I can say this PD is 6 volts. Or another way that I can express it is using the current and the resistance. So I could say 6 volts, or I could say IR. This will come in handy a little bit later on in the next exercise. But let's stick to voltage now. As I go round the circle using conventional current, I can see that this is 6 volts plus 6 volts plus another 6 volts, right? So what I've got here are 6 plus 6 plus 6. I add these up and I've got 18 volts. I can see that Kirchhoff's second law is well and truly respected because the EMFs equal the PDs. Or I could have written it as the summation of all the voltages, as in the EMFs minus the PDs, would be equal to 0, as they would be if it's 18 minus 18. Now, as I said a moment ago, it's just as easy to express the PDs in terms of the current and the resistance. So we're going to do exactly the same thing again, but this time using I and R. If we think about Kirchhoff's second law, we have summation of EMFs have to equal the summation of the resistances. So shall we see if this circuit obeys Kirchhoff's second law? Well, first, let's add our EMFs. Okay, so what have we got here? We've got 24. Ignore these minuses. They're just a different way of doing it, which I think is quite confusing. Let's do it my way. We're conventional, and what we're going to do is we're going to think about the potential. We're going to think about the EMFs. So what we've got starting here is that we have 12 volts, and we go around to find the next EMF, and there's a 24. Now, is this moving in the same direction as this is? And yes, they're aligned, right? We're going from positive to negative. So this is in the same direction. The battery's push is in the same direction. So basically, we've got 12 plus 24, and that gives us 36 volts. That is our EMF. Now let's have a look at our PD. If I look at the previous question, I can see that the current is moving this way, right? Okay, so the current through there is moving that way, and the current through here is moving this way, right? Well, let's have a look. What is the potential difference if I move it like this way? Current is moving that way, right? Let me start my loop here. I'm going to start here, and I'm going to do all my PDs. So my first situation is here. Is the current moving in the same direction as my, the way that I'm moving, yeah? It is, because it's moving that way. So basically what I've got here is V equals IR. Current is, let me have a look, 0.5. So 0.5 times 30 gives me 15 volts. And now I go to my second one, and the current through this one is in the same direction I'm moving in, right? So it's positive 0.5 times 10, which gives me 5 volts. And then I go through to the next one, and I find that the current 0.5 times 32 is 16. So I need to add those three up. 30 plus 5, 15 plus 5 plus 16 gives me 36. So yes, this does follow the second law. Now, let me show you what I mean by the difference between your direction and the current's direction. You're going to have a go at this question a little bit later once you've warmed up to it. But I'll give you an example of what I mean. If I try and answer this question, I'm going to start here, which is my positive plate, using conventional current, and I'm going to move this way. And the first potential difference that I come across is this one. Can you see that the current is moving opposite to the way I am? And by the way that I am, I mean by the way that I am considering the question, right? Basically, when I add the PDs in this question, I would do minus I3 times 20. And then here, as I'm moving up through here again, remember I have to consider just a single loop, right? Then it would be I3 times 20 plus I1 times 10. Let me say that again because I made a mistake. As I go round to look at my PDs, I would say minus I3 20 plus I1 times 10. Eventually, I will end up with a minus value for I3 if this arrow happens to be pointing the wrong way. So you really don't have to worry too much about putting the currents in the wrong way. Anyway, this is quite a hard question and you are going to warm up to it.